Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 1 on quadrilaterals. All right, we're starting a brand new unit in this lesson, right? Unit 6, which is going to be all devoted to figures that have four sides, right? Quadrilaterals. So we're going to kind of do a general introduction to these things today, and then we're going to get in them more specifically. We're going to be studying all sorts of special types of quadrilaterals and their properties. We're going to be getting back into geometry proof. I know you missed it. You know you missed it. All right, so hang on because this is going to be a fun unit. Let's start right now. Now you might need to have a calculator with you a little bit for today's lesson. There's going to be some numerical work. It's not going to be too intensive, all right? But if you don't want to be adding and subtracting things by hand, then have that calculator handy. I know I've got mine. All right, so quadrilaterals. We now move from studying triangles, which have three straight sides, to studying quadrilaterals, which have four straight sides. Broadly speaking, there are two main types of quadrilaterals. There's a lot of subtypes, but there are two main types, and let's take a look at them in exercise number 1. In the two images below, a convex and concave quadrilateral are shown. All right, so the one on the left is convex, the one on the right is what we call concave. Now let's take a look at letter A. Explain why the sum of the interior angles of either type of quadrilateral must be 360 degrees. All right, well this is really cool, right? Literally, if I take any four-sided figure whatsoever, and I add up the size of that angle, plus the size of that angle, plus the size of that angle, plus the size of that angle, I'm going to get 360 degrees, just like when I add up the three interior angles of a triangle, I get 180 degrees, right? Same thing with even this thing, this concave quadrilateral with this funny reflex angle here that's greater than 180 degrees, right? Even that one, when I add up all four of those angles, I'm going to get 360 degrees. Now, why is that? Let's understand this, because this argument can be generalized to a figure with however many sides you want, right? If I draw in a diagonal, I'm going to draw in this diagonal. Well, I'm going to try to draw in a diagonal. Let me try to do that a little bit better. Actually, I'll just draw it in like this, right? Now, when I draw that in, okay, and likewise, maybe I'll draw this one in here. All right, when I draw that diagonal in, then it breaks each of the quadrilaterals into two triangles. And of course, right, if I add up that angle, and that angle, we'll have 180. And if I add up that angle, and that angle, I'll have 180. And therefore, the sum of all six of those angles now would be 360 degrees. And the same is true here, right? 1, 2, 3 angles that would add up to 180. 1, 2, 3 angles that would add up to 180. So, explain why the sum must be 360. Right? I'll just say this: if a single diagonal, and we'll talk about diagonals a little bit more in a bit. If a single diagonal is drawn on either quadrilateral, it breaks it into two triangles. Yep, I know, I left the I out. Two triangles, each of which have angles that sum to 180 degrees. That's it. Now, one thing that can confuse students a little bit is you might have somebody come along and say, yeah, but if I drew in two diagonals, then I'd actually have four triangles, right? And you would. 1, 2, 3, 4. So then why wouldn't we just have 4 times 180, which would be 720 degrees? Well, you would have 720 degrees. The key is, though, 360 of those degrees would be contained in those four angles, right? And those four angles, 1, 2, 3, 4, are not part of the angles that actually make up the quadrilateral, right? They aren't part of it. Unlike if I delete this one diagonal and I delete that little thing, right? If I look at the three angles in this triangle and the three angles in that triangle, those three angles are each part of the angles of the quadrilateral, as opposed to like some kind of random mysterious angles that are created when the two diagonals cross here. All right, so all quadrilaterals have angles, interior angles that sum to 360 degrees, just as all triangles have interior angles that sum to 180 degrees. Now let's take a look at letter B. Plot any 2 points that lie on the interior of convex quadrilateral ABCD. Connect them with a line segment. Does the line segment lie entirely within the quadrilateral? All right, so in other words, if I just pick two random points, 1, 2, and I connect that with a line segment, or I try to connect it with a line segment, that line segment lies entirely within the quadrilateral. What if I maybe this point and this point? Well, that line segment lies entirely within the quadrilateral. Maybe if I did 2 points that were kind of close together, like here and here, well, that lies entirely within the quadrilateral. So the answer is yes. Any line segment whose endpoints lie inside of the convex quadrilateral will lie entirely inside of it. Really, the answer to this question is just yes, but I want to really kind of boil it down, right? If I take any 2 points that are inside of the convex quadrilateral and I plot them, and I connect it with a line segment, those 2 points, then that line segment will lie entirely within the convex quadrilateral. On the other hand, letter C, is the property from B also true for the concave quadrilateral EFGH? Illustrate. Well, think about this, right? If I plot any 2 points within the concave quadrilateral, will the line segment connecting those 2 points also entirely lie within the concave quadrilateral? Well, pause the video now and think about that a bit. Well, sometimes, right? You know, like if I plotted this point and this point, that would certainly lie entirely within the quadrilateral. If I plotted this point and this point, that would certainly lie always within the quadrilateral. But if I plotted this point, let's say, and this point, and I connected them, now I have a portion of the segment that lies outside of the quadrilateral. So the answer there is no. And that's really the difference between a concave and a convex quadrilateral. Or at least it's a good test to see whether something is concave or convex. In a convex quadrilateral, which by far are going to be the ones that we work with the most, okay? In fact, we won't see another concave quadrilateral after this lesson, right? But convex quadrilaterals, the whole point is that any line segment drawn inside of those quadrilaterals will lie entirely inside of them. Whereas in a concave quadrilateral, there are some line segments, right, that will partially lie within the concave quadrilateral and partially lie outside. Okay, so now that we know the difference between them, let's move on and do a little numerical work with quadrilaterals. Exercise number 2. For each quadrilateral shown below, state whether it is concave or convex. Fill in the missing angle measure. All right, so concave, convex, simple enough. if I look at quadrilateral QRST, if I drew any line segment whose endpoints lied within this, it would entirely lie within it. So this is a convex quadrilateral. Now, we are missing one angle. And this is no different than when you're missing an angle in a triangle and you're looking for it. In that case, you'd add up the two angles you know, subtract from 180 to find the angle you don't know. In quadrilaterals, it's a little bit more complicated because we have to know 3 of the angles, right? But we're going to add up those 3 angles, subtract from 360 to find our missing angle, right? We know all 4 angles have to add up to 360, so I simply add 118 to 75 to 68, right? Just want to make sure I do that all well. So let me write this down, 118 plus 75 plus 68 ends up being 261 degrees. And now I take 360 degrees, subtract 261 degrees. And I think I get 99, but let's just make sure. And I get 99 degrees. Never hurts. All right, so our missing angle is 99 degrees. Very simple, right? But you haven't done this nearly as much as you have with triangles, right? Think about how many times you've had to figure out the missing angle of a triangle and you've added the other 2 up and subtracted from 180. Very similar here, except now, because the sum will always be 360 degrees, we have to add up all the angles and then subtract from 360. Let's take a look at letter B. All right, in letter B, right, we've got now a concave quadrilateral, okay? And you can really see them, right? You got these, if you will, these 2 sides that are kind of bent inward, right? And likewise, you could do that test if I put a point here and I put a point here and I connected the 2 with a line segment, right? That line segment would extend outside of the quadrilateral. So this is now a concave quadrilateral. And I want to figure out what the missing angle is. So I'm going to take my big old reflex angle first, 221. I'm going to add to it 75. And I'm going to add to it 19. And I'm going to get 315, so let me just write that down. 221 plus 75 plus 19 is going to be 315 degrees. And now I'll do 360 minus 315. And I'll get a 45-degree angle that's missing. And I think I'll throw that on my diagram. All right, let me clear that out. And then let's take a look at letter C and letter D. All right, so what I'd like you to do now is pause the video, right? Tell me whether these are concave or convex quadrilaterals, and then figure out the measure of the missing angle. Pause the video now. All right, so letter C is again convex. And letter D, very clearly, concave. Okay, for letter C, let me get my calculator up there. I've got my 49. I've got 2 90-degree angles. That's not unusual. That's going to give me, if I can get it to enter, a total of 229. So 49 plus 90 plus 90 is going to be 229. 360 degrees minus 229 degrees gives me that missing angle. 360 minus 229 gives me a missing angle of 131 degrees. All right, so we've got that one. Now all we need to do, oh, I think we just had a ladybug friend fly into our frame. All right, now we need to just finish that last one. We already know it's concave. Big value for a reflex angle, 254. Plus 27, plus another 27, gives me a total of 308 degrees. So 254 plus 27 is is equal to 308 degrees, and now our missing angle will be 360 minus 308 degrees, which I think I can do in my head. 52 degrees. All right. So that one really reinforces two concepts, that problem, right? One, the difference between a convex and a concave quadrilateral, and two, how to figure out missing angles of quadrilaterals when you have 3 out of the 4 angles. Let's play around with that last idea just a little bit more in one more problem. Exercise number 3. In quadrilateral QRST shown below, segment QR is perpendicular to segment QT. The measure of angle S is 55 degrees, and the measure of angle R is 9 degrees more than the measure of angle T. Determine the measure of angle R. All right, fantastic. I'd like you to pause the video, play around with this a little bit. You're probably going to have to use a little algebra to figure out the answer, but see what you can find. All right, well, I'm going to mark everything that they've told me, right? QR is perpendicular to QT. That tells me that this is a 90-degree angle. Measure of angle S is 55 degrees. That's simple enough. I'll just put that there. And notice that the measure of angle R is 9 more than the measure of angle T. So if I put X here, I could put X plus 9 there. All right, and that really kind of lays out everything that they've told me in the problem. Now I want to determine the measure of angle R, which is X plus 9. But if I can solve for X, then I can just add 9 to it and I'll have my final answer. Now what do I know? Well, what I know, obviously, is that those 4 angles have to add up to 360 degrees. So if I said X plus 9 plus 90 plus 55, all of that would have to be 360. Whoops. Let's try that again. 360 degrees. All right. Now I think I'm going to combine some like terms, right? I've got my 90 plus 55 plus 9. That's going to be 154. So I'm going to have x and x, so 2x plus 54 is 360. I can now subtract 54 from both sides. Wait, I don't know why I just got 54. That's 154. Subtract 154 from both sides. That's far too small. So 360 minus 154 is going to be 206. And divide by 2 on both sides, and I'll have x is 103. And it's really 103 degrees. Now, I always have to be careful in any problem, but this happens a lot in geometry, where I come up with an answer, but it's not, unfortunately, my final answer. So, yes, measure of angle T is 103 degrees, but they asked me for the measure of angle R, which is 9 degrees more than the measure of angle T. So the measure of angle R is equal to 103 plus 9, or 112 degrees. All right, great. That's it. Let's keep going. All right, so we now want to talk about a very important feature, which are the diagonals of a quadrilateral. Now, we will work almost exclusively with convex quadrilaterals in this course. All of our special quadrilaterals, which we're going to start to dig into in the next lesson, are convex. One important feature of all quadrilaterals are their diagonals. And all diagonals are line segments that are drawn from one vertex to a non-adjacent vertex. So an adjacent vertex, well, obviously there's line segments connecting those because those are literally the sides of the quadrilateral. But for instance, A and C aren't adjacent, they aren't touching. So if we connect them with a line segment, that's a diagonal. And likewise, B and D, we can connect with a line segment, and that's a diagonal. So let's take a look at exercise number 4 and think a little bit about diagonals of quadrilaterals. In quadrilateral ABCD shown below, do the following. Letter A, draw the 2 diagonals, state their names below. All right, well, why don't you go ahead and do that, and then we'll talk about it. Awesome, this is easy enough, right? So I'm just gonna, I'm gonna take my straight edge, because I've actually given myself one this time, and I'm gonna connect points A and C. And likewise, I will connect points B and D. Now again, it's really important to understand that these aren't sides of the quadrilateral. They are simply line segments that connect vertices that wouldn't already be connected. So AC and BD, whoops, of course you could call them CA and DB. It doesn't matter, but there we have it. Those are my two diagonals. Now letter B is super simple. Let's do this one together. Mark the intersection point of the diagonals as point E. All right, that's easy. We've done so much work with intersections that you certainly should know what an intersection point is, but point E. All right, finally, letter C. Name two pairs of angles that must be congruent in this diagram and give a reason why they must be congruent. All right, so there's two pairs of angles. I can say this particular angle is congruent to this one, and this particular angle is congruent to that one. I want you to name the two pairs of congruent angles and also tell me why they must be congruent. All right, well, I definitely know that AEB is congruent to DEC. Angle AEB is congruent to angle DEC. And I know that angle AED is congruent to angle BAC. And I know that they're congruent because they are vertical angle pairs. And those vertical angle pairs are going to become important for us. Eventually, you can see this coming, right? We're going to have geometry proof where possibly the diagonals of a quadrilateral get involved, and because the diagonals will always produce these two pairs of congruent angles, they may get involved as well in order to prove that two triangles, right? Because right now we got four triangles sitting up there. Two triangles are congruent. Okay, one more problem. Quadrilaterals in the coordinate plane. We will certainly work extensively with quadrilaterals in the coordinate plane. We can use our coordinate geometry formulas, like those for distance and slope, to determine many properties of these quadrilaterals. So let's do that a little bit in exercise number 5. Quadrilateral EFGH has vertices at E, -3, 2, F, 1, 5, G, 8, 4, and H, 0, -2. Letter A, draw EFGH on the grid provided. All right, awesome. Well, pause the video now and go ahead and get the image of EFGH on that grid. All right, well, for me, the magic of the board allows me to just do that, and there's my EFGH, no problem. Now let's take a look at letter B. Prove that sides EF and GH are parallel. All right, so how do we prove that two segments are parallel? Pause the video right now and think about that, and then we'll come back and talk about it real quick. Well, parallel and equal slopes, right? It's all about slopes. Equal slopes. So if I want to prove that EF and GH are parallel, I have to show that their slopes are equal to each other. So pause the video now, calculate the slope of EF, calculate the slope of GH, make sure to show your slopes in simplest form, okay, because that's the best way to compare them, and then hopefully they're the same number. Pause the video now and see what you get. Again, be careful about your notation in situations like this. Make sure don't say something like EF equals, right? Because EF is the length of segment EF, right? What I want to do is just be very, very good about this, right? I'm going to put down EF, and I'll put a little colon after it, right? And then I'll say M is equal to. All right, so what do I have? I have the change in Y, which is 5 minus 2, divided by the change in X, which is 1 minus -3. 5 minus 2 is 3, and 1 minus negative 3 is 4, and I can't do anything with that, right? EF is got a slope of 3/4. Now, let's take a look at GH. Again, just trying to be very, very good. All right, for GH, I'm going to have the change in y, which is negative 2 minus 0, all divided by the change in, oops, no, that's not right, negative 2 minus 4, I don't know where that came from, divided by 0 minus 8. All right, negative 2 minus 4 is negative 6. 0 minus 8 is negative 8. A negative divided by a negative is a positive. And 6 divided by 8 reduces down to 3/4. And therefore, EF is parallel to GH because slopes are equal. All right, I had to kind of shove it in there, right? And again, we kind of expected that because we had our strategy up front, but it's important once we've got those two slopes to state formally EF is parallel to GH because the slopes are equal. Now let's take a look at letter C. Show that sides EF and HE are congruent. All right, well look, two segments are congruent if they have the same length. It's that simple, right? If two segments, if we're trying to prove two segments are congruent, we have to show that they have the same length. So we need to show that there's the same length using the distance formula. All right, and of course the distance formula is a little bit more complicated than the slope formula. Not a ton, but a little bit. So I'd like you to pause the video right now and try to find the length of EF. Now it would be appropriate to say EF equals, and the length of HE, again, HE equals. Hopefully what we'll find is that they're the same number. If they're not, then we likely made a mistake in our calculation. Pause the video now and go ahead and do that. All right, let's do it. So EF, what do I have? So I've got, let me just move this over here. All right, EF is equal to the square root of, let's see, I've got 1 minus negative 3 squared plus 5 minus 2 squared. Now I can move this up a little bit. EF is equal to 1 minus negative 3 is 4 squared plus 3 squared. And that's going to be 16 plus 9, which is the square root of 25. So EF has a length of 5 units. Awesome. Now let's hope that HE has the same length. Now we're losing this a little bit, so maybe I need to just write down those points real quick. Let me write down H is 0, negative 2, and E is negative 3, 2. All right, now we can take a look at the length of HE, right? The square root of negative 3 minus 0 squared plus 2 minus negative 2 squared. So HE is the square root of negative 3 squared plus 4 squared. Negative 3 squared is 9, and 4 squared is 16, and you can already probably now see how this is going to work out. And HE is also 5. Awesome. So EF is definitely congruent to HE because they have the same length. All right. We're going to be doing a lot of work like this in Unit 6, where we try to either prove or verify particular properties of quadrilaterals by using coordinate geometry. And those three major tools, right? The slope, which will tell us about parallelism and perpendicularity, the distance formula, which will tell us about distance or lengths, and finally the midpoint formula. But we're going to kind of leave that one alone for right now. All right, so let's wrap this up. So in today's lesson, we saw quite a few different things. We saw the difference between a convex quadrilateral and a concave quadrilateral. And, keep in mind, again, convex is going to be the way that we're going to be going pretty much from now on. All right, we also saw the important fact that the sum of the interior angles of any quadrilateral, concave or convex, is 360 degrees. Okay, and then we also saw how we can use things like coordinate geometry to look at various properties of quadrilaterals. Everything that we saw today, maybe except for the whole convex-concave thing, is going to come up time and time again in Unit 6. So make sure to really pay attention on the homework and nail it down. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.